So, welcome. It's amazing to see so many people. I keep saying to people, and keep pinching myself, because, for a UK-focused, very narrow subject area workshop, it's amazing to see so many people. In fact, there should still be quite a few more people drifting in, including some of the speakers, hopefully. So I'm Simon Moore, as many of you will know, and my colleague Robert Watson and I really kicked the Cherry stuff off. But there have been so many people involved, and we couldn't have done it without so much input from our own research teams and other people involved. So it's great that we're, at this point, and we're getting all of this interest. Today we've got a very full program. I realise we do occasionally make the odd glitch. It did say coffee at 9 to 9:30. Sorry about that. There will be coffee at 11, and there should be plenty of lunch. There's posters outside and a coffee break in the afternoon. In fact, hopefully there's quite a lot of cake and fruit and all sorts of things. So hopefully you'll do just fine. So I hope you enjoyed the day.
Great. Thank you very much. Good morning. As Simon says, we're incredibly pleased to welcome you here to Cambridge and see such a great turnout. When I talk about the slides, this is the building where we really kicked off the Cherry project in 2010. Small meeting room around the corner. We had visitors from SRI, a number of folk from industry who joined us, and we basically had a brainstorming session. We said, well, could you take the ideas from historic capability systems and blend them with contemporary microarchitecture, blend them with contemporary software instructions and architectures, and get anything useful at all? We thought, well, we'll give it a try. The remit and the context was DARPA's CRASH program. And the way we've sort of described that program is if you could change anything about computer systems to improve security, what would you change? Where you were allowed to really work anywhere up and down the hardware software stack, use any techniques you like. It's a very exciting research program. Lasted about 4 years from 2010 to, 2014, 2015. And we were the most conservative of the designs, right? I mean, we took for granted existing instruction sets. We kept around most of the premises of current processor designs and just dribbled in as we could the smallest interventions we thought would allow significant disruption. And then I guess here we are today. And I also want to acknowledge there are numerous sponsors who've assisted us over the years. I mean, especially of late, Innovate, the investment in ARM, Morello, and the DSPD program is outstanding. But also support from ARM directly, from Google, Microsoft, and others who helped make this event possible today. So very much appreciated. And I guess while you're here, capability systems are not a new idea. You can walk down the hall it's that way this week, and you'll find the CAP computer. So the CAP computer was completed, the project was completed in 1977. Certain of us might have been born in the year 1977, so that's sort of, tangentially amusing. You should go take your selfie and so on. I think all the bits are not there. You can't turn it on, but you're certainly welcome to look at it and make exciting observations. I mean, the principles of capabilities and privilege reduction and so on are a design pattern, right? And they're a design pattern that we've imbued into countless different types of software and hardware systems over the past 30 or 40 years. And it's not just us, right? Lots of people have done that. The details are enormously different. And in part, that's because the remit of our project was to try and do it in a way in which the technology could be transitioned. It was not a clean slate design. It was supposed to be an incremental set of changes with the opportunity for less incremental software change in the future, not necessarily the immediate implication of it. So I think a similar idea, but a very different project in some sense. So like Simon's covered this, you're in Lecture Theatre 1. This is where we'll mostly be today when we're not drinking coffee, turns up, or talking to each other, or looking at the posters and doing things like that. Conference is always true. The hallway track is often the most important part of the conference, and I really encourage you to get to know all the projects you see out there, spend some time with people standing at the posters, and use this as an opportunity to meet people and talk as much as you can. Slightly more sort of boring, but also essential, is that when you need the bathrooms, they're on the other side. If the coffee arrives, you will need the bathroom, so you'll know what to do. And the building's reception is happy to help you if you need to arrange taxis or anything like that. Simon mentioned the lack of planned fire drills today. So I want to take just a couple of minutes at the start of the event to talk to you a little bit about where we see ourselves as being in this project. So the Cherry technology is mature is a funny word, right? But it is increasingly mature. We got software demonstrators at scales of 50 to 100 million lines of code running. We have demonstrations in industrial environments, in government environments, and so on. So it's kind of an exciting moment, but it is fundamentally a very hard technology to transition. One of the reasons for that is the hardware and software design cycles, but also industrial deployment cycles are really different from each other. You go into a company like Google or Microsoft or pretty much anyone, right? We told about 9-month product timelines for software. Everything you're doing will be in this thing within a year and a half and shipping in front of customers, if not much sooner. But when you go into the hardware side of the house, 5 years, 10 years, these are realistic numbers for the deployment of even relatively incremental hardware changes. And of course, we're trying to do something a bit less incremental in that regard. The supply chains also make it very difficult. You can't, on the whole, go to one company and affect the entire end-to-end story. Instead, your OS vendor who sells your mobile phone OS comes from this place, but they don't make the phones. Those come from that place, but they don't make the chips. They come from, they don't do the processor designs. And that makes it very hard to intervene end-to-end in the supply chain enough to pull a technology like Cherry through. And then if that all weren't bad enough, it's also really hard to sell security, right? Security is hard to measure. It typically is viewed as a cost rather than a cost saving in many environments. And even where it is a cost, the tolerance for disruptive change is low. And you have only to look at things like the deployment of Rust to realize that you can have significant excitement around transformative technologies, but almost zero adoption. When we look at the size of the open source corpus for Rust, it's beautiful that 40 to 50 million lines of code in open source Rust exist today. And then you look at the amount of source code that is lying around in just one OS kernel or one web browser. So for reference, Chromium is 47 million lines of code. There is more C and C++ code in the Chromium web browser than the entire open source Rust ecosystem. So there we are, right? Excitement is good, and we need to build on that, and we should be working together on these things, but at the same time, this stuff is really hard. But with Cherry, the potential wins are huge, right? So Rust requires you to rewrite your software from the ground up to get memory safety to a large extent, and obviously like a carefully qualified claim. You're in a space of recompilation and incremental change, gradually pushing from half of the issues importing to 3/4 of them found at compile time. So that's a really amazing thing to do. If you really want to rewrite the world of Rust, which I don't discourage you from doing, you should plan to take at minimum 30 years to do it, because you can't just rewrite all the software. There aren't even the test suites to manage that today. And the amount of invested quality assurance in existing software stacks is phenomenally large. Another thing that we maybe in some sense are much more excited about, memory safety is a very 1970s problem. We're much more excited about the possibility of new kinds of software designs based on scalable compartmentalization and sharing, and trying to bring some of those ideas, which have seen very niche use today, but been very effective in fault isolation, being brought out at a much larger scale. So what do we need to do? Well, we need to identify and engage with two kinds of things. One is clear visions for how the technology can be used and deployed, things that will be compelling, that are accessible to non-technical audiences as well as technical audiences. And at the same time, we need to deal with a bunch of obstacles, and some of which are technical. This community knows how to deal with technical obstacles, right? We do research and development and experimentation and all that stuff. And, in a few years, we make some progress on these things. The non-technical obstacles are far harder, right? They are the market obstacles, the deployment obstacles, the supply chain obstacles, the things around software deployment that are entirely tangible, but are not accessible for fixing with minor C and C++ code changes. Right? So that's hard, and we need to, as a community, work on those things. And I think, looking at the successes of DSBD, it's important to understand that we've made enormous progress on the technical front, and we have made some progress on the non-technical obstacles. And those are the things which I think are now the real challenges. I think in some sense, and declare success prematurely, but many of the hypotheses of DSBD, the UK program, have been entirely validated, right? You can build large-scale contemporary microarchitectures that support Cherry. You can bring large software stacks over. Those are outstanding outcomes, but that is not sufficient to get these kinds of things on the market at large scale yet. I thought I would just touch on a couple of topics. So the first is, we're getting increasing recognition from the world's governments and security agencies that Cherry can have a significant impact. So this started, I think, really with the joint document from NCSC, CISA, and various others last year, really highlighting the importance of secure foundations to build things on. And so an escalation this spring, the White House's report on Back to the Building Blocks, in which they highlighted memory safety as a critical thing to address. And Cherry is one of the ways that we might choose to address that. A bunch of us have been meeting with the White House and CISA and others over the past year or two to try and help build confidence, but also bring demonstrators, right, to take some of the work this community has been doing into those environments and say, the time might be right? And yes, there is lots to do, but on the other hand, if you don't start now, you're never going to get to your objective. And so, it's nice. They've been putting the writing on the walls. It's very thoughtful of them, suggesting to industry that now might be the time to think a little bit harder about addressing some fundamental security flaws. But there are also some unanswered questions. And one of the ones we're going to be pushing on quite a bit in the next couple of years is actually, how do you buy this stuff? Like, how do you ask for the benefits of a technology like Cherry, or for that matter, Rust, or appropriate applications of formal methods? How do you request that in your product order form? Because I sat down with Doug Mon from the Department of Homeland Security a few years ago, like 6 years ago, maybe 8 years ago. And I said, at DHS, you want to buy notebook computers that have Cherry in them. How are you going to do that? Right? You're excited about the technology, but explain to me the steps we need to get there. And the ultimate answer was, I need a tick box on a procurement form. A tick box, you trace back through a long line of dependencies, is going to turn into things like, improvements in industrial best practice that are linked to standards that describe expectations, all that stuff. Very boring, but incredibly important. And so we need to engage with those things if we want to enable a future adoption. And it is just like rife with pitfalls. I mean, anyone who's been involved in like common criteria or any of these other like standardization efforts or attempts to get people to use stuff. But I think it's an engagement we have to have, because otherwise you're just not going to get it. There is no visible convergence with large-scale use of memory safety on the horizon. Right? It's going to be, if we're lucky and Rust takes off and it all goes really well, 30 to 40 years, maybe. But I mean, it's like, that's a long time away. You have to have a heart monitor in the meantime. You might want memory safety before that. So, and I think I keep mentioning Rust and formats and so on. I think it's important that the work we do here actually relate to all those. I mean, not least because there are different camps that believe very different things, and we need to get them to agree on some stuff. Because if you go into a room and say, we'd like to have procurement tick boxes for memory safety, and you don't agree with your other colleagues about what memory safety is, that's not going to go very well. No one's going to put that tick box on a form. So we'll work on that. We also have to reward early adoption. Like, I think it's important to recognize that although we now have much stronger technologies, we can't ignore the ones that are getting early deployment today. And some of the earliest deployments of, to be honest, Rust and Cherry in industry are happening in places that will also have been early adopters at a larger scale of those other technologies. So we need a lot of buy-in to get there. So I just wanted you to be aware of that conversation and perhaps, help engage in it in the ways that you can, because I think it's really important. And demonstration of use and an active community producing exciting things using this technology or helping us to improve the technology is going to be essential to doing that. Because I think to engage people in these discussions, you have to show the technology, if not ready, can be made ready. Spend just a couple of months on this. So you may be aware, there's mentioned at the DSPD All Hands meeting a few months ago, there's a Cherry Alliance CIC. This is a UK-based community interest corporation. It's like a baby charity, right? So you don't do quite as much paperwork, you don't get quite as many tax benefits. But the intention is to create a joint voice and space for companies and universities and others who are working with Cherry to help produce common materials, to work on, if you will, like certification activities, maybe contribute to standardization, contribute to software ecosystem enablement. You'll see more about this in coming months. I think it will launch in the autumn, and by that we mean, maybe the paperwork is not quite ready yet, but this is something we'll invite everyone we can to participate in, and hope very much you'll be able to contribute to. Use it as a tool for what you want to do, but it'll be there and available to help steer and provide some useful things if you want to contribute to that. I thought I'd also use this moment to just tell you we have an upcoming software release. We didn't really get to talk about this at the DSPD All Hands meeting. As you know, we have this derivative of FreeBSD called CherryBSD, where we've been building up and exploring as a reference design how you atom smash Cherry with large-scale software design. We've been using this basically for at least 12 years now of co-design. So we do things over and over again around here. We try all the bad ways, and eventually we find the good way. But also we're trying to, this is part of enunciating a vision. So the vision that we're describing here is one of general purpose operating systems and general purpose processors, things that run in desktops and tablets and servers, not necessarily small IoT devices. We have some beautiful visions and ideas being presented there from others in this community. David Chisnell's work, for example, leading the Chariot team, has been particularly influential in ideas about how very small devices might use Cherry, but this is our vision of maybe how big devices do. And a key part of that vision is to say, well, you can take 100 million lines of code with relative ease and convenience, adapt it for strong memory safety without a total rewrite, ideally tiny fractions of a percentage of 100th of a percent of lines of code. And then you can do it at scale and get a really usable system. One of the things we've been pushing on the last couple of years is an area of Cherry technology, which is very immature coming into DSPD, and that's software compartmentalization. And so pushing that technology forward has been a big focus for us. And in fact, our upcoming release allows you to use that at a much larger scale, which comes at the end of the program rather than the beginning. But we have some early adopters in this session who will tell us a bit about their experiences. I think, we'll take just another moment and just show you what happens when you do this kind of thing, but only very briefly, because we're already not running on time. But I borrowed some minutes from Tariq with his permission, so that is okay. So we do our presentations on Morello boxes, because if you're not using the technology, it's not real. So what you see here is the Morello box sitting here on the desk in front of me. We're doing the screen share. We don't have Zoom on Morello right now. We thought long and hard, how do you get Zoom onto Morello? And the easiest answer was to run the x86 Linux version of Zoom under an ARM instruction set emulator with an OS API. No, we are crazy, but on the other hand, we don't have that much time. So we would do it if we had time. But we could get there if we want to. Instead, it's we're screen sharing using HDMI output. And when we run uname, I can see, and maybe you can't see, that this is running an AR64C kernel. So this is a spatially memory-safe Unix kernel. I forget what the lines of code is, 10 million, 7 million, something like that, lines of code in a conventional OS kernel. Really does, just work. It's great. And when we look at our process list, kind of like down the right-hand side, there's a column here which is labeled MUL, but I think maybe in your mind, think of this as ABI, right? What kinds of things do we have running? And ELF64C means it's running with the spatially memory-safe user space. This is our Cherry ABI environment that we published about a few years ago. And there's actually an extended version of it that provides heap temporal safety as well. So if I do a bit where you try to type passwords on stage, never works out. Oh, it did this time. And we can see a few interesting things. So we can see this quarantine column here, which tells us that we're currently using memory quarantining and then a sweeping-based revocation technique to deterministically prevent use after free attacks from taking place, which is great. And we could do the thing with the debugger and show that to you, but we're not enormously endowed with time. But I want to show you the other column here, which is the C18N. C18N is a cute abbreviation for compartmentalization. You may have seen internationalization as I18N and localization. Brooks Davis's fault. But there we are. And what you can see is that we're running with a lot of compartment floating around the system. So I have an instance of, where is on this list? Ocular. Ocular is the PDF viewer in KDE. So it's running with spatial safety, it's running with heap temporal safety, and it has about 146 compartments in it. And we've selected compartment boundaries in this case as being library boundaries. So amusingly, there are 144 libraries linked into Ocular. And that is after they have decided to combine a bunch of classical libraries into big container libraries where we haven't put the library boundaries around them. This is what a contemporary application is. Like your application code is a small part of the picture, and the library code is a very large part of the picture. And those libraries are full of vulnerabilities, right? This is image processing, this is PDF rendering, there's JavaScript rendering. We have it all in Ocular. And so one of the things that I can do is attach to that using GDB. So an important part, by the way, of like these pitches worth thinking about is the realism of the thing. So I want you to just look for a moment as I'm giving the demo. I am able to take for granted a running desktop environment with all the applications up and running. I'm able to take totally for granted the existence of the compiler tool chain, natural integration into C, debugger interface, and so on. This is what other people need to have in their demos as well, and we could do it better, but we need to have that, because if you go into, for example, a national security agency of some sort, or whoever it might be, your company, and you're giving a demo, they need to know that all the supporting environment is there. So a recent thing that we brought up on the platform, you can meet my PhD student, Zhang Li, out in the poster sessions. She brought up NSA's GIDRA reverse engineering environment with Morello support, which means that we can do low-level code reverse engineering. We can look at the actual behavior of software running on top of Cherry. You can ask questions like, is this pointer still valid? And what are the bounds on it? And look at the linkage with the PLTs and do all the stuff. It's all real, which is really important. So let's set breakpoint in the ping library. So we're not yet at the point where we have those cool demonstrations of like we ran the exploit from 2022. That will come, but we're not there. But what I can do is show you a little bit about compartmentalization. So here I am in my compartmentalized application. And it's important to know, like lots of this are being rendered in different compartments. But I've set a breakpoint in the ping compartment. So sometime when I ran my mouse just over the menu bars, it decided to do some ping rendering. Don't know, maybe it was pre-rendering an icon that might have been on the menu or something. But we've gone ahead and broken here. And what I want to show you just briefly is the stack trace. So conventional stack trace, I think we've not estimated how many lines of code are in Ocular, but it's got to be like on the 20 million line side, I would guess, when you account for all the libraries. But we have some new entries in the stack trace, such as this one, which is a cross-compartment call. So two things I want to tell you about. The first is we put in compartmentalization boundaries, which have properties that we happily talk about in the poster session, allowing domain transitions as we go between independently maintained pieces of code. Are they the right boundaries? Probably not, right? They were never designed to be security boundaries. We probably want to massage the boundaries a bit to push them to better places or have robustness properties they don't have today. But they now appear on our core stack, and we can see that they're there. But there's another thing, again, take for granted. So today, when I compartmentalize an application with an MMU-based system using processes, I'm attaching GDB to dozens or hundreds of processes and independently stepping through them. And when they call from one to the other, they do message passing and they marshal things. And not only do they run a lot of very vulnerable code to do that, but I can barely debug the system. It's turned a compartmentalization problem into a distributed system problem, which makes it really hard to engage with it. Whereas now with this environment, we can just sit down and talk about compartmentalization of software at significant scale in a way that we couldn't before. I would show you just one other last thing before yielding the floor to speakers whose time I'm borrowing. Let's load the kernel module. Yes, it is. Okay, so opaque to you, but incredibly visible to me, is we're looking at the 4 cores on our Morello system. And what I've asked it to use is the hardware performance counters for domain transitions. And so in our idle system, we are routinely doing what, 20 to 30,000 domain transitions a second, just as a matter of course in our execution environment. If I were to delete the breakpoints and detach from the process, oops, I should reload that, run around, we can see that we're easily getting up into the tens of millions of domain transitions per second. This is a demonstration of the kind of thing you cannot do with conventional processor designs. If you were trying to do 10 million process context switches a second, your TLB would catch fire and all the other bad things would happen. More to the point, you would have a sluggish user experience. You'd be lucky if icons turn up every now and then while you were trying to render things. And we're just, as I said, I've been doing this the entire demo. At no point during this demonstration have I not been doing, tens, hundred thousands, millions of domain transitions a second. That's the scalability we have to have if we want to deploy compartmentalization. So I will wrap up with that and, welcome questions in the break or coffee or whatever it is, and hand over to some of our other speakers. This is a bit